This section is on series and convergence. So this is section 9.2. And in this section, what we're going to be talking about are essentially summations of sequences. So here, if we have an infinite sequence, call it A sub n, and if I take that sequence and I want to add up all of the terms in the sequence, this creates an infinite series. And again, each of these are the terms of the series. And sometimes you will see that the series will begin with 1, or an index of 1, and others might be 0, and occasionally something other than those two numbers. Okay, but if you're unfamiliar with this notation, this is simply saying the sum of the first term of this series or of this function and adding up all of the terms because it goes to infinity. Now sometimes you might have like a 5 up here. That's not going to give you a series, it's just going to give you the sum of the first 5 terms of the sequence. And we'll talk about that here shortly. So talking more about an infinite series, basically the starting value for the index must be taken from the statement. So if we're looking at what we have here and we want to find a sum, well, the notation we use for a series is a capital S, and then the subscript is the number of terms you add. So here, if this is S sub 1, we just have the first term. In this one, we're going to be adding the first 2 terms of the sequence, and so on and so forth. This part here is important. It says if the sequence of partial sums converges, then the series converges. And it's indicated in the next definition. So here's a definition. This is the definition of convergent and divergent series. Basically, it's saying if this sequence of partial sums converges, then the sum, or the infinite series, also converges. And it's shown here. Also, it's similar with diverges. So you can kind of take a few minutes to look through that definition if needed. But let's jump into an example here. It says find the sequence of partial sums right here, 1 to 5. So as mentioned in a previous slide, if I want to find S sub 1, that is simply the sum of just the first term. So it's 1. And all this is the first term of the sequence. So if I want to find S sub 2, then what I'm doing is I'm taking the first and the second term and adding those together. So 1 plus 1.5 is equal to 3/2. So all I've done here is I've taken the first term and add it to the second term. And so on and so forth. So the partial sum here would be 1 plus 1/2 plus 1/4. Adding these together, you get 7/4. 1 plus 1/2 plus 1/4 plus 1/6. So that's adding the first 4 terms. This gives me 23/12. And then here, plus 1/8. And there are a couple ways you can do this. I'm just showing you what this means. So 49/24. Okay, and really that's all there is to it when finding the sequence of partial sums. Here I'm going to introduce you to the first type of series that is quite common, and it's a geometric series. And in general, the series looks like this here. And basically, we're just adding a little bit to the function that we're working with. So this R is referred to as a ratio or a common ratio. But basically, what we're doing is we have this function, we identify what the terms are, and we add them together. So a very common geometric series is this one here. In fact, I think we may have seen it in one of the previous sections, maybe the last section. So it's nice to, again, have a list of different theorems. Since this one's pretty common, you might want to continue that list of theorems. So it says a geometric series with ratio R diverges when the absolute value is greater than of R is greater than or equal to 1, and if it's less than 1, then it converges. That's huge. You absolutely need to know it, and that's why it's illustrated by a star here. So in order to find this sum, we can just use this little formula here. The catch is you can only find the sum if that series diverges. I'm sorry, converges, as you can see here. Okay, so one thing, the R is basically the base. Okay, so we'll look at some examples of convergent series, and then we'll look at some examples of divergent. Okay, so examples of convergent series. In this first example, I have 2 times -1/2 to the n power. So this is a geometric series because it takes on that a times r to the power of n, that look or that form. And so what I want to do is I want to identify the base of n. Well, because I have some parentheses here, -1/2 is my base. So r is equal to the absolute value of -1/2, and this is equal to 1/2. This value is less than 1. So by theorem 9.6, so that was the theorem on the previous slide, since the absolute value of r is less than 1, this geometric series converges. Okay, let's look at the next one. In the next one, same type of thing. Here, I've given you several of the first terms, but really, all you need to do is look at this base and identify if that is greater than or equal to 1 or less than 1. In this case, r is equal to 0.9. This is less than 1. So this geometric series also converges by theorem 9.6. Okay, but let's look at some examples of divergent series. So they're geometric series, but they are divergent instead of convergent. Okay, so here, take a look at this. Again, this takes the form of a times r to the n. And my base here is 5/2. So this is a geometric series because it takes on this form. and r is equal to the absolute value of 5/2, which is 5/2. This is greater than 1. Since this is greater than 1, this series diverges by theorem 9.6. All right, to this last example here, we're going to look at this. So this means the absolute value of r is actually 1.05. This is also greater than 1, so you need to pay attention to the negatives also. So this will also diverge. Okay, so really identifying convergent or divergent series for geometric series is really pretty straightforward, and it's just by observing what that common ratio is. Okay, so a little bit more about geometric series. Here's some properties. Again, this is a theorem you could jot down if you want. I think these properties are a little more straightforward than some things that we'll see. Basically, it's saying if you can identify the sum of these individually, you can add them together to get the entire sum. Okay, so you can take a few minutes and look at that one if you'd like. As promised, here comes some more theorems. So theorem 9.8 talks about the limit of the nth term of a convergent series. So it has to be a convergent series. So if you have a convergent series, then the limit is equal to 0. Okay, so that's kind of nice. Well, the contrapositive helps us identify a test for divergence, and this is yet another theorem. So this is the nth term test for divergence. This is saying if the limit does not equal 0, so if the limit is not equal to 0, then the series must diverge. Okay, so we'll see some illustrations of these. Okay, so here it says find the sum of the convergent series. So if I want to find the sum of a convergent series, then according to theorem 9.6 from a previous slide, that is found by taking the first term and dividing it by 1 minus the common ratio. So for this, we need to identify what the first term is and what the common ratio is. Well, the first term is what I get when I plug in this. So it's going to be when n equals 0. So a sub 1 is really, so the first term is really when n is equal to 0, which anything to the power of 0 is 1. I also need to know r. R is the common ratio. We talked about that on previous slides. In this case, it's a negative 1/5. So we just need to plug these two things into our formula. So we get that this sum is equal to 1 over 1 minus a negative 1/5. This becomes 1 over 1 plus 1/5. Which is 1 over 6/5, which is 5/6. So the sum of this convergent series is 5/6. Let's look at another one. So here you may want to pause this and see if you can figure this one out. The tricky part in this one is I don't tell you what the common ratio is. I don't tell you what r is, but you do know the first term. So it's kind of like the opposite of the previous problem. So basically, the common ratio can be found. So R again is the common ratio. That's like, you know, what is the base of our power? Well, one way you can identify this is by taking A sub n plus 1 divided by A sub n. And this is just, suppose, think of this as the second term divided by the first term. So -3 divided by 9. Or you could think of it as the third term divided by the second term. Or you could think of it as the fourth term divided by the third term. However you think of it, our common ratio is going to be a -1/3. Okay? So if I want to find the sum of this, I'm going to take the first term. Let me write the formula down for, yeah. A sub 1 over 1 minus R once again. So the first term over 1 minus R, which is a -1/3. So this is 9 over 1 plus 1/3, 9 over 4/3. So this is 9 times 3/4, giving me 27/4. So the sum of this convergent series is 27/4. I hope you are tolerating this information okay so far. Okay, so this problem is a little bit unusual, but it's kind of interesting. It says write this repeating decimal as a geometric series and then write the sum of the series as a ratio of two integers. Okay, so if I have 0.63 repeating, this is just like saying 0.63, 63, 63, 63, 63, 63, 63, forever and ever and ever, you guys. So if you have time, you can write 63 over and over and over if you want. Okay, so what we're going to do is analyze the place value of each of these 6 threes. Okay, so for this first one, I can rewrite this as a fraction. I can write this as 63/100ths. Okay, well, if I have 63/100ths and I add that to this one, which is in the 10,000ths, so 63/10,000ths, that gives this one. That will give me these first 4 terms. Okay, well, what about this one? Well, this is 1, 2, 3, 4, 5, 6. So I need 6 zeros. So this is 63 over 1,000,000. And that will give me my first 6 digits. Well, if I keep doing this, then I'm going to end up with this number. Okay, so let's see what we can do. Okay, so what we want to do is we want to come up with some sort of summation. Okay, so let's take a look here. Now we definitely want to find R. Okay, so remember R, you need the second term and divide it by the first term. So that would be this. And divide it by the first term. If I divide this by the first term, that's the same thing as multiplying by the reciprocal. Okay, so some things cancel, these 63s and then 2 zeros. So I'm left with 1 over 100. So this tells me my common ratio. This tells me my base. So I know that when I'm going to write my summation, part of this is going to have 1 over 100 to the power of n, because that's my base. So let's give this a try. Okay, so I need to represent this somehow. Well, oftentimes we start with 0 to infinity. And if I just have 1 over 100 to the power of n, if I plug 0 in here, I get 1. Okay, so if I just have 1, that doesn't give me my first term. I need to figure out how I get this 63 somehow. Well, to get this first term, I need that. I need 63 over 100. And then I'm going to multiply by 1 over 100 to the power of n. Now, I know that this is easy for some to see, and for others it's going to take a lot of practice in order for you to see what's happening here. So just watch videos, do examples, and it will kind of pan out for you. Okay, so this is part A. Part A, right, yeah. So here it's written as a series. I suppose either of these would suffice, but this one's the more formal one. Okay, now we want to write the sum of the series as a ratio of 2 integers. Okay, so if basically I just want to find the sum, and that result is going to be a fraction. That's all that means. So remember, so this is part B, to find the sum, it's equal to the first term divided by 1 minus the common ratio. Well, our first term is 63 over 100. And we will divide that by 1 minus 1 over 100. Okay, well, this gives me 99 100ths. So if I'm dividing by 99 100ths, I have 63 over 100 times 100 over 99 by multiplying by the reciprocal. The 100s cancel. It gives me 63 over 99, and this can be reduced to 7 over 11. Okay, I believe there are some other examples you can take a look at if necessary. Here in this example, it says determine the convergence or divergence of this series. Okay, so I want you to take a look back at theorem 9.9. I'm unable to go back here, but theorem 9.9 is the nth term test for divergence. Okay, and it says that if the limit as n approaches infinity of some function, if that limit does not equal 0, then the sum diverges. Okay, so let's see what the limit of this function is. Okay, so the limit as n approaches infinity of this. Now, I'm hoping that you kind of remember this about limits. What you can do is you can compare the degrees, and in this case, since the degree of the numerator is equal to the degree of the denominator, this limit is equal to 4/3, which is the coefficients of those. This does not equal 0. Since 4/3 does not equal 0, then this is said to diverge by theorem 9.9. Okay, and I think you're beginning to notice how it will be helpful to have a sheet of theorems set aside somewhere. Okay, let's take a look at another example. All right, so same set of directions. So let's just kind of see what is happening in this particular sum. Okay, so if I have S sub n, well, here, pay attention to our index, what we're starting with here. If I want to find this, I end up with 1 over 1 plus 1 minus 1 over 1 plus 2, just plugging in 1, plus 1 over 2 plus 1 minus 1 over 2 plus 2 plus 1 over 3 plus 1 minus 1 over 3 plus 2, so on and so forth, right? Okay, well, let's simplify these fractions. This becomes 1/2 minus 1/3 plus 1/3 minus 1/4 plus 1/4 minus 1/5 plus 1/5 minus 1/6 plus on and on and on. Well, hopefully you notice that some things cancel out. Negative 1/3, 1/3, negative 1/4, 1/4, negative 1/5, 1/5, so on and so forth. So as this continues, what I end up with is this second term, whatever that may be. Okay, whatever we use to get to n. So we have 1/2 and then whatever this last piece is, which ends up just being this. And you can, kind of go through and verify, pick a couple different values. Okay, so this is equal to 1/2 minus 1 over n plus 2. And it's nice to be able to simplify this, because now if I apply this limit that we've been talking about, we can see that if this is infinity, the denominator is increasing faster, so this approaches 0, leaving me with 1/2. Okay, so in this case here, we will say that this series converges. Okay, so you're probably thinking, what the heck just happened? All right, so let me kind of explain this a little bit more. This series is known as a telescoping series. And it's a pretty common type of series, and what that means is kind of what I illustrated before, all these terms cancel out. Okay, well, and you can read about this on page 600 in your text if you like. But basically, a telescoping series converges if this sum is equal to this. Well, our sum is, in fact, equal to that first term, so it converges. Okay, so something a little bit different. Okay, let's look at the next example here. It might be helpful to rewrite this using properties of logarithms. So the natural log of 1 over n can be written as the natural log of n to the negative first power. Remember, we can take that exponent and move it in front, so this becomes the negative natural log of n. Okay, so maybe I want to find the first several terms of this. Okay, so S sub n is equal to, okay, well, looking at this, I'm starting with 1, so this is negative natural log of 1. Now, I can write plus a negative natural log of 2 every time, the plus or negative, but it's really going to be subtracting every time. Okay, so let's see what we get. Well, in this case, natural log of 1 is 0. Now remember, the natural log graph looks like this. So the natural log of 1 is 0. So this sum, if I take all of these and I add them all together, this is going to approach negative infinity. So in this case, the limit does not exist, and so this is said to diverge. Okay. Now, this is basically it as far as, determine the convergence or divergence of the series. I highly recommend that you watch the CalcView videos, you look at the examples in the text, because these are the types of problems that you're really going to have to see a lot of examples in order to wrap your brain around it. Okay. This last example is kind of an application type problem. It says a ball is dropped from a height of 16 feet, and each time it drops h feet, it rebounds 0.81 h feet. Find the total distance traveled by the ball. So to be a little more clear, we want, okay, so if the ball is dropped here, this is 16. What's going to happen is the ball is going to come up and back down, and then it's going to come up to 0.81 of that height, to 0.81 of that height, so on and so forth. Okay, and what we're looking for is this distance that it travels. Okay, so now it's important to know that originally that we drop that ball 16 feet. Okay, so to find this other distance, we're going to apply this. Okay, so we are starting here, okay, on this little hump. Well, to figure out this distance, to get from here to here, I'm taking 16 times 0.81. This is like the upswing of the ball. Well, to get this distance, the downward part, I'm going to take 16 times 0.81, because whatever goes up needs to come down that same distance. So this is the down part. Okay, well, this gives me this little first hump, if you will. Okay, so I can add this together, or I can write this as, how do I want to write this? 32 times 0.81. Okay. All right, well, let's do the next one. Let's look at this little hump here. Well, let's call this D sub 3. Now I need half of this height, or not half, but 0.81 of this height, which is what we had here. So we know that now, oops, sorry, hang on. Now we are going to go 0.81 of this. So this is up. Same thing for the distance down. And I can write this as 32 times 0.81 squared. Okay, well, this is showing us that when I add all of these together, I'm going to end up with a geometric sequence, because this takes on a sub n r to the power of n. So this becomes, adding all of these together, 16 plus this plus this, on and on and on. Well, how can we write this? Well, the way we write this is the following. Now, we want to be careful with this first distance, because really we don't want that first distance. We need to make sure we subtract that out from the rest of the sum, because it's not the distance that we need here. Okay, so then we're going to have the sum. We're going to let this be 0 to infinity, and we need to figure out what this is. Well, it's pretty much written for you here. The only thing is we need to make this exponent an n. So this is 32 times 0.81 to the power of n. So in order to find the total distance traveled, I just need to evaluate this. I need to find this sum. So negative 16 plus our first term then will be 32 divided by 1 minus 0.81. Find this sum and you should end up getting 152.42 feet. And that wraps this up.